Okay, so today we're going to continue to talk about connectedness. So last time we were focused on the following definition. A space X is disconnected if X can be expressed as U union V, where U and V are non-empty, disjoint, and open. So to kind of warm up for this lecture, I want to start by mentioning a characterization of connectedness. So connected is, you're connected if and only if the only subsets of X which are both open and closed are the empty set and X itself. So subsets of X which are both open and closed are sometimes called clopen, for the obvious reason, closed and open. So the only clopen sets are the empty set and X. So let's see why this is true. This is basically just by definition. I mean, equivalently, X is disconnected if we phrase this in terms of the negation. X is disconnected if and only if there exists some U in X, which is clopen, and U is, well, it's non-empty and proper. So, I mean, U is not empty or X. But of course, this follows directly from being disconnected. When you're disconnected, you have two open sets. Since V is open, its complement, since V is open, its complement is closed. So U and V are both clopen sets here. And similarly, so that's basically how the forward direction goes. And conversely, if you have a clopen set, which is non-empty and not everything, then its complement is also clopen. And so then X is disconnected. It's the union of U and its complement. So as a consequence, so last time we proved, R is connected. And so this implies the only, the only clopens in R are the empty set in R. Okay, so open sets in a topology have a strange property that, well, sets in a topology, they don't have to be open or closed, but they can also be both. But if you're connected, then the only sets that are both open and closed are the empty set and the whole space. Okay. Maybe I wanted to give one more example. Of course, you can look at maybe I don't want to do this example. Okay. Yeah, let's do one more example. Sorry. So you can look at this connectedness property for different topologies on a given set. Let's look at the set with 3 elements, and let's consider these two topologies. So the first one is this one. And the second one is this one. Okay, so looking at these, we want to decide, are these connected or not connected. And well, here we can see that here we have these two disjoint open sets whose union is everything. So this is disconnected. Here you can't do such a thing. The only proper open subsets is this one, and its complement is not open. This is connected. There are no non-trivial Clopin subsets here. Okay. So now the main topic for today is path connectedness, which is, well, let me start with the definition. So a path is a continuous map from the unit interval into X. And we say X is path connected if for every pair of points P and Q and X, there exists a path alpha which starts at P and ends at Q. So that alpha of 0 is P, and alpha of 1 is Q. Okay, so so we'll draw pictures like you have P and Q, and a path is well, it's a path. Okay, so some examples. Rn is path connected. Given P and Q, well, you can consider there's a straight line from P to Q, which has this formula. So this is so the vector Q minus P is exactly this vector, and well, okay, so okay, that's straightforward. Another example, the sphere Sn in Rn plus 1, these are points of distance 1 from the origin. This is also path connected. So let's prove this. So fix P and Q. Well, the thing we want to do is, well, here's what we're going to do. So we have 2 points. They're somewhere, P and Q. And we want to find a path between them. And I mean, pictorially, this it's sort of evident that such a path exists, but let's see how to do this a little more explicitly. So given, oh, sorry, so let's consider the plane V that spanned by P and Q. So this is a copy of R2. And V intersect Sn, this is a copy of the circle. So in this picture, there's the plane spanned by P and Q, which intersects the sphere in a circle. And so on that circle, what we see is we have P and Q. And we can choose an arc connecting them on the circle. Okay, and that circle is contained in the sphere. And so this is exactly what we want. Okay. Right, so one of the reasons we're interested in path-connected spaces is if you can show a space is path-connected, then you know it's connected. So X path-connected implies X is connected. So let's prove this. So by contradiction, suppose that X is disconnected. And so we can write it like this. And let's take U and U and V and V. So they're non-empty, so we can find some points like this. And X is path connected, so we can find a path and alpha to X, a path from U to V. So then, and then, well, so now the problem is that, well, let's consider alpha inverse of U. Well, okay, so what this gives us is the unit interval is a union of alpha inverse of U and alpha inverse of V. These are open because U and V are open, and they're non-empty because 0 is in here, and 1 is in here, since 0 maps to U and 1 maps to V, little u and little v, and they're disjoint. This implies that 0, 1 is disconnected, which is a contradiction. Okay. So as an application, okay, before that, so let me remark that being path connected, this is a topological property, since if F is a topological equivalence from X to Y, and well, right. If Y is path connected, then X is path connected, and vice versa. I mean, if you have 2 points in X, well, okay, this is easy to see. So if Y path connected, this implies X is path connected. So if you, let me just draw a picture to try to convince you of this. So if you have, let's say A and B in X, well, then you just map them over to Y, you get f of A and f of B. Those are connected by a path, and then take the inverse of f to get a path from A to B. Okay, so all right, so we're building an arsenal of topological invariants or topological properties, which we can use to show that spaces are different. So far we have, well, most recently we have compactness, connectedness, and now path connectedness. And so as an application, we can show that R is not topologically equivalent to R squared. So to see this, okay, so let's suppose that for a contradiction that there exists topological equivalence. So I want to alter this slightly so that it sends the origin to the origin. So let's set G to be, so G of X is f of X minus f of 0. So here G of 0 is 0. So now, then G restricts to a map from R minus 0 to R squared minus 0, which is a topological equivalence. Restriction of a continuous function is continuous. It's a bijection because G is a bijection, and we threw out 0 and its image. Okay, so now, well, on the one hand, R minus 0 is not path connected. Let's say not path connected because it's not connected. And on the other hand, R squared minus 0, this is path connected. Because, well, if I remove the origin, even if I remove the origin, I can still connect any 2 points by a path. I mean, you can use a straight line for most points, but if the 2 points are on some line through the origin, then maybe you have to go around, but that's no problem. So this is a contradiction. So on the one hand, we said if R and R squared are topologically equivalent, then R minus 0 and R squared minus 0 are topologically equivalent, but this can't be because one is path connected and the other is not. Okay, so we conclude that R, so therefore R is not topologically equivalent to R squared. So I want to look at one more example with path connectedness. I want to return to the topologist sine curve. So I claim that, so let's call this X. X is not path connected. And in fact, as we'll see in a second, we'll argue that, so okay, here's the picture of the topologist sine curve. Sorry. We'll see that in the argument that no point over here can be joined by a path to some point over here, which maybe agrees with your intuition. But before we say something about this claim, let me just remark, so consequently, so last time we showed X is connected. And so this is an example of a space which is connected but not path connected. So in general, path connected implies connected, but this reverse implication does not hold. Okay, so that's why one reason why this example is interesting. So let me say something about the claim. So the sketch of the claim. So let's set Y to be this left edge here in the picture. This is Y. And let's let alpha be a path in X with alpha of 0 in Y. Okay, so consider some path that starts at some point in Y. And now the claim, which maybe I shouldn't have two claims here. Let me call this proposition. So now we claim that, well, if you have a path that starts in Y, then it's in Y for all time. There's just no way that it's going to venture out to the right. So the image of alpha is contained in Y. That's the claim. And if we show this, then X is not path connected, because then any path starting in Y ends in Y and hence can't end in some other point in X. So to prove this, it's enough to show that alpha inverse of Y is clopin. So if we show alpha inverse of Y is clopin, this is a subset of 0, 1. We know that 0, 1 is connected. So the only clopin sets, hi, sorry, got a little friend here who wants to be disruptive. The only subsets of 0, 1 which are clopin, since 0, 1 is connected, the interval, are the empty set and the full set. Now, alpha inverse of y is not empty because alpha is a path which starts at y. So 0 is in here. All right, bye. So if all right, so if we can show it's clopin, then it has to be everything, which would prove the claim. Now, okay, so what can we do? So first of all, alpha inverse of y is closed because y is closed and alpha is continuous by assumption. So the inverse image of a closed set is closed. It's not hard to show why is a closed subset here. The complement is open. I think I mentioned that in the last time this example came up. And so we want to show alpha inverse of y is open. Right, so here's how we can do this. So let's fix t in 0, 1 with alpha of t and y. So what we want to say is that, so okay, we have t here. We want to say that if s is close to t, so we have some s, then s also maps into y. So the reason why this is true is, well, so let me get a new page. So there exists a ball around alpha of t so that, let's call it BR, so that BR intersects X is a disjoint union of arcs. And here's the picture. So we're at some point here, alpha of t, and if you choose a small enough ball, I'm going to draw it kind of big, but what does it look like in a neighborhood of this ball? What does the set X look like in a neighborhood of the ball? So you have the segment that's part of Y, but then you have a bunch of other segments, whoops, that come through. Well, it's a graph, so let's see. Pass through here infinitely often, but you get these disjoint arcs. So by continuity, there's a small neighborhood around T so that the image of that neighborhood, so here we have T, and so this is in 0, 1. Let me call this, sorry, this is getting, I think I can call this U safely. So we know that alpha of U is contained in this ball, B sub R. By continuity, but T gets sent to this point here, and the map is continuous. And so the only way that this is possible is if all of U gets sent into this interval. I mean, because the open interval U is connected, and well, we have these disjoint union of – I'm not sure I'm explaining this very well, but this is the picture. Maybe I will leave you to think about this a little bit more. Right, so I wanted to sketch this, but maybe I'll leave you to think about the full details. So in this way, you can show that alpha of y is open. And so then it's alpha inverse of y is everything. So the whole map maps into y. Okay. Maybe that's all I'll say about that. So the last thing I want to say is right. So we're in the process of doing a bunch of point set topology. And there's basically one more topic that I want to cover before we go in a different direction. And that is what's known as quotient spaces. So these are important examples of topological spaces. And in particular, so to motivate them, we're going to use these to give a rigorous definition of the Mobius band as a topological space. Right, so let's consider the Mobius band. So let's start with x, the square. And we know that we get the Mobius band by gluing these two boundary pieces of the boundary together. So the way to do that rigorously is to define an equivalence relation. Which says that, so the point 0, comma, y is equivalent to 1, comma, 1 minus y. So this specifies the gluing. So 0, y, and 1 minus y. And so this specifies an equivalence relation. So every other point, so all other points are in their own equivalence class. And so we'll set M to be the set of equivalence classes, which we'll denote like this, set of equivalence classes. And so theoretically, this is what it means to glue. So you define this equivalence relation, which says, well, in the product, these 2 points are different, but under this equivalence relation, they're the same point. Okay, so this is the type of thing we want. And what remains is to define a topology on M. And so we want a topology on M. And well, we want this topology to satisfy the property that, well, the natural map from X to M is continuous. Right, I mean, if there's any, seems hopefully like a mild request. If we're going to put a topology on this set, this map should be continuous. And well, one thing we can do is we can force this by declaring that V in M is open if, let me give this map a name, P inverse of V in X is open. Okay, so if we do this, then if we declare such V is open, then this map is going to be continuous. So of course we need to check that this actually defines a topology so that the axioms are satisfied. But right, so I don't want to do that now. Let me instead draw some pictures. So what would the open sets look like? So let me draw some open sets. So let me use some colors to indicate the edges that are glued. Let's say these glue up to this edge here. So here's some open sets. So you could take, if you take a small ball here, its pre-image is going to be a small ball here, which is open. The interesting thing happens near this edge here. So, well, we kind of want the Mobius band to be a surface, so to look locally like R2, maybe away from the boundary. So we would hope that some set like this is open. And the pre-image of this set, well, what does it look like? So it looks something like there's a little piece over here, and then there's another piece over here. And indeed, this is an open set of the square with the subspace topology in R2. So, okay. So next week, we will take a more formal look at quotient spaces and show that in this case, and more generally, if you define a topology like this, then it actually is a topology. And we'll look at some more properties of this type of construction. All right.